Hello everyone, my name is Zhao Shixiang, and I'm a PhD from St. Petersburg State University. My instructors are Professors Yuri Petrov and Grigory Volkov. I'm very pleased to share our research with you here. And the topic of my presentation is the analytical study of the non-monotonic behavior of dynamic yielding diagrams. Many temporal phenomena of high-rate plastic deformation of metals, such as the yield drop phenomena and subsequent non-monotonic behaviors, or the oscillations of the stress strain diagram, were found in many experiments under rapid tension. These phenomena cannot be explained by the existing classical models and theories of plasticity. Thus, the modeling of the irreversible deformation diagram under dynamic loading is an actual and important problem. There are plenty of high-rate plastic models that can establish the stress-strain relationship of various materials. One of the most commonly used models in computational mechanics is the Johnson-Cook model, which consists of three multipliers corresponding to the Harding law, temporal effects, and temporal effects respectively. 7 empirical parameters are introduced in the Johnson-Cook model. Although many engineers have widely known this model and its modified models, they still cannot simulate many temporal phenomena observed in the stress-strain diagram. Hence, Yuri Petrov proposed the so-called relaxation plasticity model, the RP model, in 2015. Based on the integrated phenomenological criterion of plasticity in the form 1. The integrated inequality 1 determines the yield condition of materials for an arbitrary pose of loading. The introduced time parameter, tau, which is called the incubation time parameter, is independent of the specific features of deformation and sample geometry. It can predict the behavior of the yield stress of materials sigma y under static and dynamic loads. It was shown that the incubation time could be related to different physical mechanisms of plastic deformation. It is assumed that the incubation time parameter can take different values depending on the initial defective structures of the material. Two independent parameters of criterion 1, which are tau and alpha, characterize the rate and amplitude sensitivity of the materials respectively. One dimensionless relaxation function, gamma, which varies from 0 to 1, has been proposed to satisfy the identity 2 at the plastic deformation stage, where Ty is instant of the onset of the macroscopic plastic flow, and it is determined by equality 1. The relaxation model is finally shown in the form 3, while beta is Harding parameter. It has been shown that the RP model has a good description and prediction ability in modeling plastic formation diagrams with or without the yield-drop phenomenon. However, for some materials, such as metals, a good corresponding with experimental data can be observed only in a strain range of less than 10%. Consequently, an incremental relaxation plasticity model, the IRP model, has been considered as a modified RP model. First of all, we introduced a dynamic stress intensity and an incubation interval as a functional. Therefore, the integrated dynamic criterion of plasticity becomes the inequality 5. Secondly, instead of the Harding parameter beta, a Harding law beta of time has been taken into account in the relaxation function gamma of time. Then, according to the RP model, the IRP model had the form 7, consisting of two multipliers describing the Harding law and the temporal effect. Considering the development of plastic flow, we redefined the function capital sigma of time as the incremental stress predictor. At the plastic deformation stage, we separate the time axis into intervals with the same length h, and on one interval, the function capital sigma of time is defined by the express 8, where sigma of time is the stress we obtained on the previous intervals. So capital sigma of time depends on the past development of plastic flow. Furthermore, on current interval, an elastic increment of stress has been proposed. However, the incremental stress predictor is not an exact continuous function because it depends on the current interval. Thus, the second multiplier of the IIP model is not continuous. Consequently, it is reasonable to introduce a continuous piecewise linear function, b of time, based on the considered second multiplier. Comparing the IIP model with the Johnson-Cook model, we take the Johnson-Cook-Harding law into our model. So finally, we have the following incremental relaxation plasticity model with 6 parameters, 3 of which are associated with the Harding law, and the others connect with the temporal effects. Now let us consider the non-monotonic behavior in the stress strain diagram of dual-phase high-stress steel DP800. Experiments were carried out at room temperature by Cadoni on a split Hopkinson bar in the range of strain rates from 10 to the power of -3 second to the power of -1 to 500 second to the power of -1. Moreover, experimental data are illustrated in Figure 1. The solid squares were obtained at dynamic strain rate, and hollow diamonds were obtained at the static strain rate. As we can see, the U-drop phenomenon and subsequent non-monotonic behavior of the stress strain curve are detected. The solid lines built by the RP model have a pattern corresponding with experimental data than the dotted line built by the Johnson-Cook model. In addition, the IIP model is better than the RP model in modeling the non-monotonic behavior of DP800, as shown in Figure 2. Figure 3 shows how functions beta and b vary with time. In the case of a constant strain rate, the production of these two functions will give us the stress strain curve. Modelings were also performed for aluminum alloy 2519A at room temperature and static and dynamic strain rates using the IIP model, Johnson-Cook model, and RP model. The results are shown in Figures 4 and 5. It seems that the better coincidence to the experimental data is reported for the IIP model. At least this model is able to explain the U-drop phenomena and oscillations of the yielding diagram for the developed process at the same time. Here are the conclusions. In our research, predictions of strain rate sensitivity of the material by different dynamic plastic models are reviewed. The dynamic stress intensity is introduced as shown here. The IIP model is considered. It takes the dynamic stress intensity, the Johnson-Cook-Harding law, and the past development of plastic flow into account. At the end, a comparison of the IIP model with the Johnson-Cook and RP models is carried out. It seems that the better coincidence to the experimental data is reported for the IIP model. Thank you for your attention.